Okay. So welcome everyone to this Nordita Niels Bohr Colloquium. I'm Mikael Fogelström. I'm the director of Nordita, and it's my pleasure to welcome you to this colloquium. We hold these Niels Bohr Colloquiums once in a while connected to programs or other events, and it's a possibility for our different activities of theoretical physics to reach out to all physicists. So the goal is to have a real colloquial and understandable talk here. So today we have Professor Stefano Liberati from SISSA who will talk about analog gravity. And Professor Liberati got his PhD from SISSA with Sjarma, and he's now professor in astroparticle physics at SISSA. He's also the president of the Italian Society of Science of General Relativity and Gravity, and director of the Institute of Fundamental Physics of the Universe. And today you'll talk about analog gravity. So the floor is yours.
Thank you. And thanks everybody for attending this colloquium and for being here this afternoon. I'm honored to be able to give this Niels Bohr Colloquium, and I'm really delighted to be here at Nordita, which is a fantastic institute to be at. So today I'm going to try to convey some general aspect of a field of research which is called analog gravity. It's a relatively recent field of research. It's no more than roughly 40 years old. And I will also try to illustrate some of the features of the lessons that we have learned so far from this field. So let me start with just a prelude, a kind of disclaimer. When I mean analog gravity, I seriously mean analog, in the sense that I'm not going to discuss gravitational system per se, but I'm going to discuss systems that mimic some of the crucial features that we're interested in gravity, and may help us shaping a kind of understanding of what may be, what are the mechanisms that can be behind some of the puzzle that currently we are facing with gravity and in advancing in gravitation theory. So in a slight sense, analog gravity is a tool. Is a tool for theoreticians, at the same time is a possibility for experimentalists, especially in condensed matter physics, to predict and test new phenomena that otherwise would not be searched for. So let me try to start with the simplest example of analog gravity. So unfortunately, it's cutting the upper part of the screen because it is not but I don't see it on my screen. I see it on this other screen. Okay. So the simple example is basically acoustic gravity. So what it is? It was realized by Bilur in 1981 that there is something interesting going on in hydrodynamics. So it takes a perfect and envisaged fluid, a rotational envisaged fluid, and consider basically the continuity in the other equation. If you neglect viscosity and you impose irrotationality so that the velocity can be written as the gradient of a scalar, which is called the velocity potential, what you can do is that you can say, okay, let me consider perturbation over a background. I have a flow, and I consider perturbation on this flow. What is happening is that you have two linearized equations that you can put together to get a second order equation, and you can eliminate basically a perturbation in the density. The density and pressure are related by the baryotropic equation of state. So you basically can eliminate with the continuity equation, for example, the density perturbation in favor of the velocity potential perturbation. And what you get is basically the equation of propagation, the D'Alembertian on a curved spacetime for a scalar, which is the perturbation in the velocity potential. This metric is not a flat geometry, it's not the lab geometry, it's a curved geometry, it's called the acoustic metric. This acoustic metric is not the most generic metric you can have in general relativity, because all the spatial sections are by construction flat. Of course, you can do more complicated models in analog gravity where this constraint is not more there. But at the simplest level, this is the structure of the so-called acoustic geometry. But you see, this acoustic geometry has a factor here, the component of the metric, the G00 component of the metric, that can go to 0, for example, when you have the velocity of the flow is equal to the speed of sound. So this immediately was recognized by Urru that in principle you can simulate black holes with this kind of geometry, simple enough, but complicated enough that you can simulate a black hole. Of course, a black hole for what? For sound. So he called that dumb hole, but then he was forced to change the title because of it was not considered it was considered offensive. So the same analysis can be done in a relativistic fluid. In that case, the acoustic geometry takes the form, for those of you that are familiar with this, of this formal geometry. So basically you get a geometry which is a flat Minkowski part plus twice the gradient of a scalar, which are substantially the four velocity of the fluid. Okay, so moving on, I told you that you can build black hole, but it's pretty intuitive how you can do that. We can see black holes of this sort in nature. So what is happening is that if you have a radial flow, for example, that is going in a sink, and at some point is moving faster than the speed of sound, if you take, for example, a graduate student with which is emitting with a sonar, and you throw it in the sink, the graduate student, you will hear something like, oh, because the waves of the sonar, once they cross the sonic horizon, are tilted so much that they cannot reach the exterior. So it was soon understood that many of the quantity that we associate with black hole can be associated as well with acoustic black hole. In particular, you can talk about the surface gravity, which is, if you want, for those of you which are not so familiar with black hole, the simplest way of thinking of it is if I am from infinity, I'm lowering something toward the black hole, what is the acceleration that I need to give to this object, to a unit matter object, to just over the horizon? Here is just the derivative along radially, so perpendicularly to the acoustic horizon of the velocity of the flow, but if the sound speed is not constant, you have to take c squared minus v squared in the derivative, not just the velocity. Of course, it has the dimension of an acceleration. You can also simulate flat space, you can also simulate cosmological metrics. And there are basically two ways of doing this. One is that let expand your fluid, or another one is that you can control in some condensed matter system. I don't know if there is people which is working with Bose-Einstein condensate here, but for example, in Bose-Einstein condensate, you can use a magnetic field to control the scattering length. That is with the VI so-called flashback resonance that control basically the speed of sound in that system. And what you can show is that controlling the speed of sound, you can simulate basically the expansion, the cosmological expansion. So you can describe a conformally flat metric with an acoustic geometry, and this was done pretty early in the history of analog gravity. So another point that I want to bring home is that given now I gave you basically in the first example, but there are many systems that are producing this sort of analogy. It's really a mathematical analogy. What you have, normally you look for system where perturbation propagates on an effective geometry induced basically by the property of the underlying condensed matter system. Most of the work has been done with some system like water, like Bose-Einstein condensate, which in some regimes behaves like superfluid, helium-3 superfluid, but there are also optic fibers analog, as we will see. So there are many applications of this very same idea. If you want to have a comprehensive, basically rendering of this, there is this living reviews of relativity, which being a living reviews is updated every now and then. The first version was 2005. The last version was 2011, which was a while ago. And I'm happy now to announce that it's going to be, the new version is going to appear this fall. So wait for this fall. There will be many citations. I mean, citation in the sense, we have to cite more than 1,200 articles just to give an idea how the community has exploded since 1981. So I also I think it's nice to see how things start up, how a branch of physics, basically, of research starts. And I want to say, I mean, here, I just want to say one thing. Very often you think you find something new and somewhere someone had already thought about it, as we know very well. And indeed, the first paper that is quoting basically an effective geometry emerging in a condensed matter system was a paper by Gordon in 1923 talking about basically the propagation of light in the electric media. You can use the refractive index to see that there is an effective geometry felt by light. But the real start of analog gravity was in 1981, as I said, with Urru. And immediately after, well, 10 years lagged, but then Jacobson came up, was at the time interested in the so-called Transplanckian problem for black hole, with which we will talk in a few slides. But basically, he was interested in how Hawking radiation works in black hole. And he understood that analog gravity could be a well-defined setting where you don't only know the theory, the quantum field theory of a recurrent space-time, but you know also the UV completion of this theory. So he had the idea to try to use analog gravity to explore this. Matt Visser in '93 basically gave a dictionary to translate from a relativistic black hole to acoustic black hole. And then there were several other proposals in the 90s about analog system. But you see, look at what happens after 99. You see the density of things that I need to list are increased enormously. And the most interesting part of this is that not only there were a lot of theoretical developments, but there were, for example, in 2007, a first experiment based on gravity waves, not gravitational wave, gravity waves, basically waves of water in a shallow basin that was used to study tsunamis in a lab, which saw basically the first mode conversion in a kind of stimulated Hawking effect, something that is not really the Hawking effect, but in a certain sense was the first experiment showing that something concerning the Hawking effect could be said in analog gravity. And then there were several developments in Bose-Einstein condensate, also on the theoretical side. And then there was, in 2009, a first experiment claiming to have seen a kind of classical stimulated Hawking radiation in a shallow water basin. So this is the Vancouver experiment, 2009, by Van Furtner, Biluru, and others. And then there were other experiments that took place in BC. And in 2019, basically with reinforcement in 2021, there was a final experiment seeing really quantum Hawking radiation, the analog Hawking radiation by phonons in a superfluid, in a special kind of superfluid, which is a Bose-Einstein condensate. And nowadays there are many experiments, and the field basically now is more driven by experiment than by theory. And this is quite remarkable because in 40 years, it's also a community where theory and experiment now dialogue a lot. And when there is a meeting in analog gravity, there is a very strict collaboration, which is something not so common nowadays in theoretical physics. I just want to give other two examples. One is shallow water basins. So this is the metric. Unfortunately, my pointer is and the battery is dying. But this is the shallow water basin. You see that metric over there, which is felt by gravity waves. There is a dispersion relation which is modified, which is basically relativistic only at low frequency, and that we will see low wave numbers, and we will see this is a characteristic of this system. But you can also do quantum system where it's meaningful to quantize the perturbation. And one that was proposed is use optic fiber. You send a pulse so that you modified locally the refractive index. You see, this is a local modification of the refractive index, which is higher inside this pulse. And then if you send another photon, a bunch of photons with a laser, basically, and they arrive here, if they come from the back of the pulse here, the refractive index is larger, they slow down, they cannot enter the pulse from the back. So this part is like a white hole, it cannot enter in the pulse. But if they're inside the pulse, they cannot escape for the front because they're slow with respect to the exterior. And so this is a black hole region. And you can try to simulate basically phenomena related to Hawking radiation in this system. I just want to, for fun, give you another thing. So in gravity waves, I told you that is a system where you have this analog metric, and the velocity of sound in this system goes like the square root of the gravity acceleration times the 8 of the basins. This is something that probably you studied in physics 1, I don't know, the first course you did in physics. Now, you can build, I don't know, if you want to show up with your partner, you go basically home, and you go at the kitchen sink, you put a flat plate under the tap, and then you open the tap, and you try to not make it turbulent. What you see normally, you see a kind of a ring where the flow splashes, right? This ring is a white hole, because what is happening is that the water is flowing outward with a velocity which is larger of this square root of GHB, because it's very shallow, the flow. And a white hole is the time reversal of a black hole. If in a black hole, nothing can escape, in a white hole, nothing can enter. And here you see, I mean, it was done a proper experiment. This is me in my kitchen sink. And you can see it at work, the same effect. You can try, you can show. So here you will see that if you try to push perturbation inside this hole, they are repelled because it's a white hole. And of course, where the flow is supersonic, you have a Mach cone, like in here. And here you see it. If you are inside, you have a cone. If you're outside, you don't. And this cone is exactly sin theta C over V. So if V is smaller than C, sin theta cannot be larger than 1. And so you don't have the Mach cone. Okay? So this is a trick if you want to show off at home with friends, if you're drunk enough. But so now let me move now to Bose-Einstein condensate. It's not that they are, well, they are special, but in the recent year, they have become one of the elective systems to look at, because they are systems which are very easy to control. Experimentally, incredible advancement have happened. I remember talking with 2 people in early 2000 about doing some experiment and discovering that initially at the time it was considered impossible. Then you discover that after 10 years they could do much better than we have ever dreamt. So in a certain sense, experiments are moving faster than theory in this field. Let me see how analog gravity works in a Bose-Einstein condensate. So in Bose-Einstein condensate, you have an n-atom, a large number of atoms, and this large number of atoms are described by many body of Hamiltonian that enters basically in a nonlinear Schrödinger equation that you see here. And what is happening normally is that we want to, in a Bose-Einstein condensate, what happens? All the atoms, most of the atoms goes in a ground state, and they sit there. So normally a trick to describe this system is to say, okay, I do a mean field approximation. I say the operator that describes the atoms can be basically split in an expectation value over the ground state, time plus excitation, quantum excitation, okay? So you have basically an expectation value, a C number, which is called the wave function of the condensate, but is actually C number, plus quantum excitation. Note that in this system, what is happening is that you have the vacuum, the ground state is not the vacuum of the atoms, it's full of atoms. So what you call, so there is this duality between the ground state for the excitation with respect to the ground state for the atoms. The two can be related by a Bogoliubov transformation. Now, what we can do is that we insert the mean field approximation in the original equation, and we have an equation for the background, so for the wave function of the condensate. And we have an equation for the excitation. They are coupled through these objects which are correlators. They're called anomalous mass and density. The anomalous density is n tilde, and the anomalous mass is m tilde. Normally, what people does is that they neglect these terms. They say, okay, these are subleading, let's throw them away. So the first equation become an equation for this classical object. It's just a nonlinear Schrodinger equation because you throw everything which is on the right, which is proportional to kappa, and you get what is called the Gross-Pitayevsky equation, which is normally the fundamental equation for physics in Bose-Einstein condensate. The other equation is the equation for the excitation. And if you throw also this extra term, what you can do is that you can introduce a Bogoliubov transformation. So basically change representation. If you instead of an operator describing atoms, you go basically in a representation where you have these two other operators. Basically, it's a trick to diagonalize the Hamiltonian of the excitation. And what you get is that you get this couple first order equation with a differential operator, which is the quantum potential. If you neglect the quantum potential, you put together the two first order equation and you get back the D'Alembert over curved background. Why? Because basically when you neglect the D2, you are basically in the limit where you treat the Bose-Einstein condensate as superfluid. The superfluid is in Vichy, irrotational. The theorem I gave you at the start works, and you find the acoustic geometry. So this acoustic geometry is describing the propagation of phonons over the condensate. Now, you may not neglect the D2 term, and in order to handle it, basically you look at high frequency particles, and then you can basically replace it with a power in K, and you get a modified dispersion relation. Look at this dispersion relation. It's telling you that at low wave number, you have a phonon, which has a relativistic dispersion relation with the speed of sound replacing the speed of light. At high wave numbers, you have a correction, which is a kind of acoustic Lorentz breaking. Interestingly enough, if you are so high that only the second term is dominant, you immediately recover the dispersion relation for a non-relativistic atom, E equal P square over 2M. So you may say, okay, but then the analogy is not perfect. But the analogy not being perfect, we will see in a second, is crucial. It's really the interesting part of the problem. Because here, this modified dispersion relation provides, in a certain sense, a UV completion to your theory. And it may be, and it came up, it turned out to be exactly what you want to see to explore, to understand some of the puzzle, for example, with Hawking radiation. Okay, and this, by the way, exactly was part of the community in analog gravity moved to start doing a constraint on Lorentz violation exactly because of this kind of physics emerging in this condensed matter system. Okay, so let me move on and talk about the robustness of Hawking radiation. So the robustness of Hawking radiation has to do with the fact that it was an open issue, the fact that when you trace back Hawking radiation, you see, when you collapse the star, light rays are squeezed basically by the collapse and reach infinity. And we observe at infinity, fortunately this pointer is dying, you observe basically Hawking radiation. But the problem with this picture, as Urru immediately pointed out, is that if you look at basically at two different instants of time, and you look at the frequency along one of these rays, take one of the blue rays, you see the red dot, what is happening is that when you compare the frequency along the ray as you trace it back toward the horizon, it exponentially increases. Kappa here is the surface gravity of the black hole that I discussed before. So what is happening? Thank you. So what is happening here is that this exponential growth of frequency risks to break down your field theory. Uh-oh. Well, I can do with the buttons. It's no problem for me. I can. Okay, so it breaks down the theory. So at the time, we are talking about the early 90s. It was basically a problem which was bothering people. It looks like you needed to have a UV completion. You need to know that your field theory works up to the Planck scale, beyond the Planck scale, to say something here. The black hole is really a microscope. It magnifies the vacuum at past infinity and produce the Hawking effect, which is an infrared effect at future infinity. You go from ER to UV. So how is possible? How we can be convinced that Hawking radiation is insensitive to the UV physics that is that you get in this way? Normally, just a caveat, some people say, oh, you can boost away a frequency, a high frequency, but here we have an S wave. You cannot boost away an S wave, okay? So, and you can also work with scattering, cross-section between falling matter and the escaping Hawking quanta, and you still see objects which are blowing up. So this Trans-Sankyan probe was exactly the motivation that started up the whole business, and by the way, in the 90s, as I already said. So in Bose-Einstein condensate, it is possible to do analog black hole. There are many ways that were envisaged. The one that worked better was to basically do a waterfall of atoms that become supersonic above a given limit. But in principle, you can take a flow and a stationary, static situation and just change the speed of sound on the two sides to generate an acoustic horizon. And it was seen in experiment, as I said, in 2021. This is the correlators between the Hawking pairs. 0 is the horizon. If you take a positive, is outside of the horizon, negative inside. So when you see this mustache here, this is the correlation between two particles, one outside and the other inside. And this is exactly what is predicted by the Hawking effect. This fringe that you see here is a kind of dynamical Casimir effect due to the dynamical formation of the acoustic horizon. And this was seen effectively in an experiment. And it was also tested that the temperature observed was fitting the Hawking temperature, though it was lasting for a relatively short time. There were several regimes in the real experiment. So Hawking radiation was seen, but then again, why is robust against the fact that in principle you're exploring UV physics? So the point is that in this case, what it was understood via Bogoliubov calculations or relating asymptotic vacua was basically that you need three ingredients. You need the separation of scale. The surface gravity of the black hole, which is the one setting the Hawking temperature, should be very different from the scale of Lorentz breaking, lambda. Very separated. It should be low energy scale with respect to lambda. Also, you need to have a regular vacuum at the horizon, so that you don't want to generate a configuration which has a kind of firewall at the horizon. And you also realize that the horizon becomes a stretched horizon. You cannot resolve, for example, the horizon better than the Hilly length of the condensate. That implies that basically you always average on a region. It's not point-like the horizon, which generates also a natural cutoff. So here I will use this kind of dispersion relation. And now I want to try to explain how does it work. So let me take a flow. This is the acoustic geometry again. I take a flow where somewhere the velocity of the flow is equal to -1. That is the velocity of sound in this. You see, I replace the speed of sound here is constant equal to 1. And I take -1 because this way the geometry corresponds in general relativity to the one of a black hole. So you have a subsonic region and a supersonic region of the flow, and here you have the acoustic horizon. And this is just a model of the velocity. Now, what is happening is that normally you relate asymptotic vacua, but you can also have a picture which is due, let's say, to Frank Wilczek and Parikh, which is basically the idea that the standard idea of Hawking radiation is that the tidal forces at the horizon are splitting up virtual pairs, and you have two quanta. And these two quanta, they must go shell, but they must go on shell with opposite energy because energy must be conserved in a stationary spacetime. Nothing depends on time. But this is possible on the interior of a killing horizon because what is energy? A change meaning due to the change in the nature of the killing vector, which from time-like becomes space-like inside the killing horizon. So normally the idea is that you split these pairs, they go on shell, and one flies inside, one escapes. But you can also revert the picture and say, okay, I can instead see this quantum as a positive frequency quanta that tunnels out of the black hole by quantum tunneling. Normally, from inside the black hole horizon, you cannot escape classically, but quantistically you can. And you can compute the tunneling rate probability if you do what is called a WKB approximation. So you basically analyze you basically take an approximation where you describe your particle as a ray that is moving with some classical action as 0. You can define what is the conserved energy along the ray of this particle. And once you have the action, you can compute the tunneling probability, which is basically the exponential of the imaginary part of this action. And if you do it for a Schwarzschild black hole, you find that kappa of r diverges as you go close to the horizon, exactly for the same reason I told you before, that there is this infinite peeling around the horizon. And then you get basically that the tunneling rate is e to the minus omega over t. This is like a Gibbs factor with a temperature which is proportional to the surface gravity of the horizon. This is what you get relativistically. Now you can play the same game with the modified dispersion relation we have. In this case, the complication is that you have the energy which is conserved, which is defined with respect to the lap time, but you have a notion of energy, of momentum with respect to the system at rest in the fluid, little omega and little k, and they are related in this simple way. If you have done some hydro, you probably have really seen that. And now we have a modified dispersion relation coming from a modified Gordon of this sort. This is the modified dispersion relation. And I am considering this factor psi so that I can discuss superluminal or subluminal dispersion relation at will. And if you put basically this expression inside this expression, you get this equation. And now you can find the root for this equation if they're telling basically the modes that can propagate on this flow. And now you see how many modes you have depends on the sign of this factor, which is the velocity square minus c square. So it depends if you are inside or outside the horizon. You put all together, and I plot here in the axis, I put the velocity flow so that this is independent on the particular shape of the velocity flow that I'm using. Instead of using x, I use v of x. And let's take the superluminal dispersion relation. What you have is that instead of having the two rays that are approaching and asymptotically the killing horizon, I have a mode that is turning around here and one that escapes and a mode that falls in. So here I have two modes, and here I have four modes because I have two branches of this turning mode, 1 and 3 and 4. And basically, there is a mirror situation in the subluminal dispersion relation case. So if you look now at this, there is no pole. Before it was crucial that in order to have the imaginary part of the action to give me a result, I needed to have a simple divergence of kappa of r. Here I don't, because they don't basically stack there. So what is happening is that in this case, however, you can always take an approximation. You can say, okay, if I take the blue modes here, the regular mode, the one that crosses, and I invert the group velocity, I discover that I can basically mimic the virtual Hawking pairs, both inside and outside, and with the difference that now I have an accumulation point at some effective horizon, which could be slightly inside or slightly outside the killing horizon, depending basically on the sign of the dispersion relation. So you discover that there is a way to make an approximation that brings you back to have a pole somewhere. It's like you're saying, okay, it's like I'm expanding both this and this close to this imaginary horizon, imaginary in the sense apparent horizon, and I forget the fact that they deviate later on. You say, okay, but they deviate. So why this approximation work? We will see in a moment. The fact is that if you buy this approximation and you describe this trajectory now, and you do the tunneling calculation, you find out that there is a temperature. This temperature is the one that you would have in the relativistic case, plus a correction that goes like alpha square. Alpha is the killing energy of the ray divided by the scale of Lorentz breaking. So what is happening here? It's happening that you have a very robust temperature, because alpha square alpha, in order for the dispersion relation to be reliable in the condensed matter system, has to be much smaller than 1. So alpha square is a very tiny correction. It's telling you that you have a very robust result. And the point is that why it works, even if there is in reality they deviate. It works because you can think in this term. When a Hawking quanta becomes really an Hawking quanta when it goes to shell. When you take a virtual pair and separate it more than the Compton wavelength, right? Because only there you can say that they are really distinguishable are elementary particle on shell. So you can say, okay, if the point at which my approximant, this blue trajectory I have used for my calculation, deviates from them is smaller than the Compton wavelength, in a certain sense, I'm in a regime where I cannot distinguish the two things. And this is always true, basically. For alpha small, is always true. So you see, the lessons here is that there is no Transplanckian problem in Hawking radiation, simply because when you start to see the UV physics, it doesn't matter, because the point where they go on shell is ruled by the scale of the horizon, because when they go on shell is ruled basically by the scale of the effective horizon. And when they go on shell, it doesn't matter what is happening here. You could put not just, you can put a dissipation, you can put other deviation from standard physics. It will always be insensitive to this. So this is, it was one of the crucial lessons for analog gravity. But let me try to do something more now and to attack the information loss problem. Because you see, once you know that an analog black hole can radiate Hawking radiation, or more or less like it would do with the same temperature it would do in Hawking radiation, you can also check that this Hawking radiation, who is paying the bill for this particle creation? The kinetic energy of the flow. So if the flow loses kinetic energy, the point where it becomes sonic, it becomes smaller and smaller. So what is happening is that it shrinks, and you can prove it. You can basically do a back reaction of the Hawking radiation in the first of the equation I show you, the one that we were neglecting, the anomalous mass and density, and I was telling you that it becomes the Gross-Pitesky equation for the background. You can use that, not to neglect them, put them back from the Hawking radiation and calculate the back reaction. It's your own geometrodynamics there. And you see the black hole shrinks. But now if the black hole shrinks, it can evaporate. And also I can always simulate a singularity in analog gravity by just creating a region where the flow, the hydrodynamic approximation breaks down and I need to record two atoms. So all the ingredients that generally go in the information loss problem are there. So the information loss problem is exactly that if I take a slice of space-time early in the life of the black hole and late after the black hole is evaporated, there is no way to evolve a pure state here to a pure state here. There is no unitary operator that is linking the two of them, because you start with a pure state, you end up with just a thermal bath. But it's related very much to the evaporation of the black hole and the presence of the singularity here. This diagram, in a certain sense, is crucial in order to get the information loss problem. So in a Bose-Einstein condensate, however, is a quantum system. There cannot be any information loss problem. So I can build an acoustic black hole in an analog system, let it evaporate, and nothing should happen. It should be completely unitary. So what is going wrong? What is going wrong is that in order to see the unitarity, at some point you have to see the atoms. The problem is that there are regions in this analog black hole where the hydrodynamic approximation breaks down. In the language of gravity is where the semi-classical approximation to space-time, classical space-time and quantum matter breaks down. So what you can do a description of the Bose-Einstein condensate, which is not relying on the mean field approximation I showed before. This is the natural orbital description. Basically, it's a description where you start from correlators, you expand them, and in this description, you have the extraction and creation operator, which are also acting on the atoms in the condensate. So in a certain sense, you have a description that sees the whole Hilbert space of the atoms, the one in the condensate that for you are quanta of space-time, and the one over the condensate, which are the quanta forming what you would call the matter over this space-time. And what is happening is that with this formulation, you can recast the analog gravity equation. And at this point, you can say, okay, what is the particle creation doing on this background? Now, Hawking radiation with this formalism is too hard to do. So we did cosmological particle creation in expanding universe. And we describe basically particle quanta creating in this universe. And the result is that for the correlators, for the quasi-particle operators, what you find is that there is an increasing number of correlation, which is due to the fact that basically the particle production process basically takes atoms in the condensate and promotes them to excited atoms, so to create the analog of the particle, of the cosmological particle creation. So what is happening is that you have also, at each time, the creation of correlations which are suppressing the number of atoms which are in the condensate. So what is happening? You are every time you have this particle creation, you are correlating atoms in the condensate with atoms, with excited atoms, which are what you call the matter over this space-time. So you have correlators which are, however, suppressed by the number of atoms in the condensate. In cosmology, this is huge, would be huge, because are all the atoms in the quantum gravity theory of the universe. But in a black hole, this is a number, and 0 is finite. And as the black hole shrinks, and 0 is smaller and smaller. And so these correlators are more and more important. So in the process of particle creation, you are neglecting, when you are taking the semi-classical limit of space-time, correlators between the object in the Hilbert space of quantum gravity and the object in the Hilbert space of the quantum matter, which are increasingly important as the black hole keeps evaporating. So this is also visible in the fact that if you prepare a state at the start and in state, which is factorizing stuff in the condensate part and the quasi-particle over the condensate, after the process of particle creation, it doesn't factorize anymore. Now, when you take the limit, the semi-classical limit, and you replace the space-time, the quantum space-time with the classical space-time, you're losing all these correlators. Simply, you're losing it. But if you don't lose, you don't neglect them, you see there is a squeezing operator. There is an operator that is unitary, that describes the evolution. The evolution is always unitary on the whole Hilbert space of the condensate. And what happens is that when you replace the space-time with a C number, with the Hilbert space of the space-time with the classical expectation value, what is happening? You lose these correlators. In principle, this is not breaking unitarity, but it's a problem once you ask the question, what happened at the end of the evaporation? Because there, all your Hawking quanta, the Hawking partner will have hit the singularity, and they will become part of the substratum, and you lose track of them if you replace the space-time with a classical object. And that is the lesson basically from Bose-Einstein condensate, that what we call the information loss problem in black hole could be simply a semi-classical artifact. It's due to the fact that we pretend to solve a problem that needs quantum gravity to be solved. So, which doesn't imply, however, that maybe there is the possibility to use semi-classical quantities to reconstruct what we are missing, which is an open opportunity. Finally, and this is the last application I want to discuss, has to do with the cosmological constant. Because, again, in a Bose-Einstein condensate, if you have this sea of phonons over your analog space-time, in principle, you compute the 0-point energy and then cut off it at the typical cutoff, which is the Hilly length of the condensate, the same length that was entering in the acoustic Lorentz breaking. But of course, you will get a huge vacuum energy, which is incompatible with observation. It doesn't happen anything strange in the Bose-Einstein condensate. So what is going on here? The problem is that what it gravitates in analog gravity. So let's go back to the first of the equation, the perturbative equation, the one describing the dynamics of the background, and let's not neglect the anomalous mass and density. This is a non-relativistic equation. The question is, maybe this can be described as a gravitational dynamics, but if it's a non-relativistic equation, it should be at most a Newtonian dynamics. So in order to have Newtonian dynamics, and however, I cannot work with massless phonons. So you can slightly modify the theory at the soft U1 breaking term that basically give a mass to the phonon. This is just a trick. There are systems where you can do this. Now, you have given the mass to the phonon. In principle, they gravitate, so you can have an analog of Newtonian dynamics. So this, if we are right, should be reducible to an analog of the Poisson equation. Nabla square of the gravitational potential equal 4 pi g Newton, the density of the phonons. Is it possible to do so? Well, in order to do this, we needed to identify the gravitational potential, which we did, the analog of the gravitational potential. And then once you know the analog of the gravitational potential, you say, if I know can I cast my equation for my geometrodynamics in this form? And the answer is yes. You can basically introduce the gravitational potential and look at what you get if you have a bunch of phonons sitting there. There will be always a part which is, let's say, the 0 point part of the phonons, and there will be the real phonons. And what you get is that, you get that exactly the background equation for the gravitational potential deduced from your acoustic geometry takes the form of Newtonian gravity, but it will be with the graviton which is short range because of the Hilly length, and as naturally a cosmological constant. This cosmological constant is directly related to the fact that when you have a condensation, it cannot be perfect. There is always a gas of atoms that is back reacting from as a cloud of atoms, which is not in the condensed phase. And the back reacting is the depletion factor in the jargon of condensed matter. In fact, it's proportional to the density of the atoms times a cube, the scattering length, which is the typical scale of their interaction. And you have also an emergent Planck energy. You see, the interesting point is that you have an emergent cosmological constant and an emergent Planck energy. Their ratio is very small. That means that the cosmological constant is very small with respect to the emergent Planck energy. Albeit is the cosmological constant which is associated to the natural scale of the system. Is the Planck energy, which is anomalous, is larger due to the combination of the parameters that enter into it. Here, the only fundamental quantity that is true also for us is h bar. G Newton is emergent, you see, with the one that enters in the Planck energy and even the speed of sound. So this is telling you that in an emergent system, if your spacetime emerges from a substratum, so you have different layers of reality. You have GR and quantum field theory, the standard model. You may have some effective field theory, which is modified gravity or a complement of or beyond the standard model physics. And then the idea here is that you have something like a fundamental layer, which is discrete and quantum. And if you are in a setting like this, and from this layer, both gravity and matter emerge, then you see what happens. You have that the cosmological constant cannot be determined by looking at the 0 point energy of the excitation over the emergent spacetime. You have really to recompute what are the analog of the geometry dynamic equation, the Einstein equation. Now you can say, can you do it relativistic? If you do a relativistic BC where the atoms are relativistic, what do you get? And you do the same path. You get this. You get the Ricci scalar of the acoustic geometry plus lambda equal 25 G Newton T. Now, this starts to look like very much like Einstein equation. This is a form of gravity which is called Nostrom gravity, proposed in 1913 by Gunnar Nostrom. And the equation of motion, this equation of motion and the Einstein-Fokker equation. It was discarded because all the metric in the system are conformally flat, so you don't have the deflection of light. But what is telling you that it's very natural that once you have this geometrodynamics, it will take a general relativistic form. Why you don't get Einstein gravity? And you cannot get Einstein gravity because in analog gravity, you always have, in a certain sense, a container. You don't have full background independence. Here, you have basically the causal structure of the flat geometry in which your lab resides. So you have basically a geometrodynamical equation, which is very much what we expect. By the way, lambda in the non-relativistic case is negative. Here is positive, plus the negative correction that make it small, can make it small. So it's just to tell you how far you can go. This is not a program which is alternative to quantum gravity, but is a program that is telling you that in a certain sense you can get to a geometrodynamics familiar to what we know if you emerge the system, the universe from, when you emerge the universe from something discrete and quantum. So I'm coming to my conclusion. And my conclusion are basically that the lessons, I hope that I've convinced you that analog gravity is teaching us are relevant, are useful even for people not interested in analog gravity. So the first lesson we saw is the robustness of Hawking radiation. How does it work? It's basically showing in a case in which we know the UV completion of the theory, is showing you how you don't need to describe the atoms to go to the full quantum gravitational system. There is no, you cannot access basically the Transplanckian physics, because in the way the Hawking effect is done, if the black hole is macroscopic with respect to the scale of the quantum gravity physics, basically the Hawking radiation will be insensitive once you have a regular vacuum established at the horizon. I'm happy to answer on this question if someone asks me why we expect to have a regular vacuum there. The second lesson has to do with basically the information loss problem. And it's just the fact that in principle, you can, as a phononic observer, you may be lured to think that there is an information loss problem also for your acoustic black holes, but there isn't once you understand basically that particle creation on an acoustic geometry always create correlation between the substratum, the atoms in the condensate, and the Hawking quanta. And these correlations are more and more important as the evaporation goes, and you cannot neglect them for the final answer. And the third lesson has to do basically with what gravitates. You see, the problem of a cosmological constant, part of the problem is what gravitates. In a system of emergent gravity like this one, it's basically teaching us that you have to redo your calculation. You have to rederive from scratch the geometrodynamics to see what gravitates. You cannot just say, okay, I take the 0-point modes of the matter on this system and then add it on the right-hand side of the Einstein equation. So these are just few of the questions that can be answered. And I want to stress that in a sense, analog gravity has also done all these works in experiments that is quite independent from this question, because in a certain sense, the techniques in the labs are advancing so fast. But I just want to mention there are many other things that we can ask. For example, what is the entanglement between two phonons? You can entangle two phonons. People can do that. And now you can do a measure on one and see how the other flips. But what happens from the microscopic point of system? What is this? What is happening? Because you see, the notion of causality between the fundamental system and the emergent one doesn't need to be the same. Actually, it's not the same. So this is just an example of how many other questions, deep questions we can try to ask. It's not obvious that reality will be working in the same way, but at least it's a training field for our understanding of what would be an interpretation of what we observe at this level if reality has a deeper level, which is quantum and discrete. Thank you.
Thank you very much, Stefano, for this very nice and stimulating talk. So we can open the floor questions. We have Niels, so I will just walk around and give you the microphone. So just be patient.
Thanks for an interesting talk. Question about the last part where you showed the emergent Newtonian gravity and then in the next emergent relativistic version with the Nordstrom. Maybe it went a little bit too fast for me. Like what? But is there an analog speed of light that you can then dial to go from one case to the other?
Yes. Okay. So, aspetta, I'm not sure I understand your question. So for sure, yes. In the non-relativistic case, there is a speed of sound. There is also a speed of sound in the relativistic case. The relativistic case is very interesting because you saw what happens. You have relativistic atoms in the UV, which are propagating with the speed of light. In the deep infrared, you have phonons which propagate with the speed of sound. And when you go in the middle, this speed of sound interpolates in such a way that it becomes the speed of light. So at the intermediate stages, you have a space-time which basically has an energy-dependent speed of sound and interpolates. And an interesting part is that you have a curved geometry in the infrared. But when you go up, your geometry becomes Minkowski. So gravity disappears, and you just have relativistic atoms in Minkowski.
Interesting. Okay.
So it's quite interesting. In order to recover the relativistic result, you may ask me, but how is possible that you recover a theory of gravity like Nordstrom gravity, which doesn't break Lorentz invariant? The problem is that you have to put yourself in a corner of parameter space in such a way that basically you don't, your speed of light, your speed of sound becomes equal to the speed. It doesn't depends anymore on energy. So you have to put yourself in a kind of corner of the parameter space. I'm not saying that this is totally natural, but it's just the point that in principle you can do it. And in that case, it's remarkable that your metric exactly becomes conformally flat. Then you basically see that from the equation of the hydrodynamics of the background, you pop up this one, which is quite was surprising also for me, because this is really the trace of the stress energy tensor of the phonons.
Is Rinat?
Thank you for the talk. So I remember reading Jacobson's article where he says that the solution to Trans-Planckian problem comes from mode conversions of ingoing modes to outgoing modes.
Yes,
so I was trying to understand.
It's exactly the same. Look, let me go. Let's look at this diagram. You see, normally you can take this, forget now with the here is say the effective horizon, but say that this is the killing horizon. So normally this would be the trajectory of the relativistic particle. They accumulate, as you trace them back, they accumulate there. What happens when you have a modified dispersion relation, superluminal or subluminal? You have a mode that turns around, so it's converted. What the mode conversion Ted was talking about is this. And basically you have that, take the subluminal case. Normally you go here and you would expect to hit the Trans-Planckian regime here. But before you hit the Trans-Planckian regime, you turn around. Now the problem is that a priori it's difficult to understand why you have still the Hawking effect, no? But the problem is that this deviation, you can still do an approximation and say, okay, I insist that I draw I take this trajectory and I prolong it, and you can do it very easily by inverting the group velocity of the regular mode that we saw before. And then you say, here I can carry the standard tunneling rate, and I find and of course you find the same result with the Bogolyubov coefficient, and with the experiment, now we have seen it. But the problem is that all the deviation where it doesn't matter. I mean, this solved the Trans-Planckian, but at the same time, it doesn't change dramatically the effect, because you have the horizon setting the scale, and then basically the particle becomes real here. They don't become real here. They go on shell when they are sufficiently far away. There is a black hole quantum atmosphere. Particles are not created at the horizon. They are created actually closer to 3M than 2M. They go on shell, of course, Schwarzschild, of course.
Yeah. Regarding the information loss problem, or the analog version of it, you said to properly understand it, you need to go beyond the mean field approximation.
Yes.
And resolve the condensate. And I was wondering if you stick with the mean field approximation. I mean, is there some signature you could still obtain, some avatar of that breakdown, and then could you hope to see something similar also in the semi-classical approximation we apply in gravity?
Good point. But so you're saying, if I stick with the semi-classical approximation that in condensed matter, in this case called the Bogolyubov approximation, then you say, can I still see some signature that this approximation has to break down? Most of the people will tell you that is the fact that you get a unitary violating result, but I don't see, you see, it's exactly the same situation we live in. Imagine we are the phononic observer. Normally people, what it does, they say, okay, I have this information probably because the black hole evaporates and I cannot recover the Hawking quanta inside. So they try to purify the Hawking radiation by correlation before it evaporates. But then you have a firewall because you are not exactly in an Uru state and so on. The problem is that apart from the unitarity, is not anything else. We haven't seen anything else that is telling us, but we have conjectured. When we conjecture, I don't know, for people that knows this, the page curve, that means that the entanglement entropy has a maximum and then decreases. You are basically saying that from some point on, there are correlators that I've been neglected that I cannot neglect. Normally, people try to make these correlators between late Hawking quanta and the late Hawking partner. But what if the late Hawking partner are not there later, but they fall into the singularity? They are basically part of the substratum once you enter in the black hole. They are associated to the Hilbert space of what you call quantum gravity. So if you are able to do that, so my answer is that I don't have an intuition of any other signature apart from the fact that it's unacceptable that you have unitarity value. And in the case of the Bose-Einstein condensate, It's not a matter of debate if there is unitarity. There isn't. It's an isolated system. We are making our calculation with the number conserving, so we don't lose atoms. So they don't have an atom that can be. So there is no way the quantum information is lost. But nonetheless, it looks like it is lost if you do the Bogoliubov approximation and you let the black hole evaporate.
Thanks.
Well, thanks. So is there also an analog Bekenstein-Hawking entropy?
Okay, so Bekenstein-Hawking entropy, it means that there needs normally, for sure there is an analog of an entropy proportional to the area because you have entangled pairs of phonons, you have a state which is squeezed, so you can compute entangled entropy. Now I think you are really referring to the entropy that enters in the first law of thermodynamics. The problem is that the first laws of thermodynamics is strictly related to the fact that you have the Einstein equation or the equation for a background independent diffeomorphism invariant theory. Think about, I mean, there are derivations. You can derive basically for any different invariant theory a first law and recognize the entropy, that is the world entropy. And that is always what generalized for other theories of gravity, the Bekenstein-Hawking. So my answer is no, there isn't a priori, because the first law is embedded in the Einstein equation. So here the geometrodynamics is different. It's not background independent, truly. It can be at most very close, like in Nostrum gravity, but still you have the causal structure of Minkowski space. So for example, in analog gravity, you cannot create time machine. You can, like in GR, you can't, because it's basically, it doesn't bend, the space-time is too rigid to generate the causal paradoxes and stuff like that.
Thanks.
With some caveat that if you have a system where the time in the lab is the time in the analog system is not the time in the lab, but is a space in the lab, then you can do it. But that is pathological. So it's just a caveat. I just say that you can do trick, but they are not relevant for my comment.
Magdalena?
Thank you for a fascinating talk. I have a question a bit on the flip side problem of the information loss paradox. And that is something that people discuss in the context of the relativity part, how and whether the horizon gets formed, and what are the conditions for the horizon to get formed, whether you see radiation before it's formed, and all. I'm assuming you are aware to some extent about this discussion. So I wonder whether there is some scope to explore the process of formation of the horizon in some non-trivial way in these analog systems, because it seems to me that the main difference is that in gravity there is one force that essentially forms the horizon and the evaporation sets in, while in the analog systems there is some external, say, drive for that. What would be the hope to resolve that other problem too? Thank you.
Okay, thanks. So it's a very interesting question. Actually, in an analog system, of course, you drive the system out from outside. You basically manipulate the potential in which your flows reside in order to dynamically generate an acoustic horizon. Nonetheless, it's very important, this. I mean, of course, so the question if the horizon form is out of question because you want to form it. You decide you can control fully the flow. However, it's very relevant if you start with a flow which is static, and then I make it flow, for example, in a sink. Now, you see, I was talking about the regularity of the vacuum is a crucial ingredient to recover Hawking radiation. But if I have this dispersion relation that basically doesn't create an infinite accumulation, in principle, I could regulate vacua which are normally singular in relativistic physics, like the Bulwer vacuum. So why don't get the Bulwer vacuum, but I get the Ur vacuum, the one that gives you Hawking radiation, the one that for some observer falling in is vacuum at the horizon crossing. The problem is that nature likes to save energy. It doesn't like a Bulwer vacuum, even regularized, will have a firewall at the horizon. It would be a very high energy state regulated by lambda, by the scale of Lorentz breaking. So at the end, if you do it dynamically in analog system, you see also that there is a natural selection of the vacuum. And if you go also for Lorentz breaking gravity, theoretically, you see that Lorentz breaking gravity has another even smarter way to tell you that there is only one regular vacuum. So it's very interesting. It's another story that would deserve a completely different talk. But in a certain sense, this is a very interesting ingredient, the fact that the regular vacuum, how the onset of the regular vacuum is related to the dynamic. In general relativity, to close up, it's very difficult to avoid the formation of the horizon in a stellar collapse, because as long as your collapse is in free falling almost, what you can do is that you climb your star and you can keep renormalizing your stress energy tensor. And if you start from a Minkowski vacuum, basically it's going to be always approximately zero, because you go in the local inertial frame. If you state, it allows you to renormalize at each step, basically you will stay in the vacuum even at the horizon crossing, and that is the Ur vacuum. And the Ur vacuum is the only non-singular vacuum when there is an horizon. So it's all self-consistent. The only way you can get out of this story is that if your star collapses so slowly that it's quasi-static, and then a vacuum polarization can, but there is nothing we know that can slow the collapse that much. Of course, if instead you have you form the black hole, you have a singularity at the center that is regularized, then you bounce, then you can also end up with an ultra compact horizonless object. But this is a different story.
Thank you for the talk, but I think my question is almost the same as the previous one. So, but so as I understand, there's no good way to model gravitational collapse in this analog systems, right? Or dynamical formation of metrics.
Yeah, but the experiments are not much focusing on that, because in a certain sense it's easy to do the generation of a dynamical generation of acoustic horizon. And the problem is that the dynamics, not being the one of general relativity, people doesn't see very much of a point. What you learn is always not the.
Okay, but maybe another question. Are there ways to model also some other kind of exotic metrics, say the shock waves, for example, in these analog systems?
Oh, okay, this is another question. Well, shock waves in a Bose-Einstein condensate cannot be present, not because there is daily length. So when you try to create a shock wave, you have a strong repulsion due to the quantum potential. That is important when you have very high density gradient. But you may ask another interesting question. Can you simulate a Kerr black hole, a rotating black hole in analog gravity? And the answer is that you can simulate slices of Kerr, but you cannot simulate the Kerr geometry. You see, the Kerr geometry can always be cast in a form which is the flat metric plus basically the product of twice a null vector. That is the so-called Kerr-Shield form. But the analog geometries that we can do, for example, relativistic fluid have the flat metric plus twice a time-like vector, which is the force velocity of the fluid. And basically, we realized that you needed to add the vorticity to simulate Kerr, which makes the system much more complicated. But you can get close to simulate Kerr. So that is presently one of the limits of analog gravity, because you cannot exactly simulate the Kerr geometry due to this foundational. Of course, if you have an analog gravity system where the force velocity means is a photon fluid, then maybe you can do that, because you can cast the analog geometry in the Kerr-Shield form. Okay.
So how far can you take the analogy to entanglement between the phonons and sort of get some sort of page curve and you know, perhaps even simulate some old black hole after the page time?
That is a very good question. Actually, we have tried, must confess, we have tried to do the calculation for the black hole geometry. Unfortunately, you know, going from cosmology, where you have an homogeneous and isotropic geometry, where you have just the scale factor dependent on time, that is the only variable, going to the analog, a black hole geometry is a mess. And we haven't been done that, because if we didn't succeed so far, but if we would, then is exactly the point. You have this correlator. These correlators should give you that the entropy in the radiation that is not increasing arbitrarily, because at some point, if you look at them, they will you will start to have that basically there must be a conservation. It goes from the Hilbert space of the gravity to the one of matter, and as the black hole shrinks, this correlator become more and more relevant. We know for sure that the 10-0 is exactly the number of atoms in the area of the black hole. And that would give you, as a possibility to give a patch curve, but we didn't succeed so far, too complicated. Also because you see this formalism is very heavy. Probably the problem is the formalism. One should try to find a better, a more manageable formalism to describe the Hilbert space of the atoms in the condensate. I might guess, but we tried. It's exactly with the idea that you would propose.
Is there any more question from inside the room?
Thanks, and thanks for the talk. So there is this series of papers from Ogievetsky in the 70s where he shows that the diff group is actually the minimal extension of two finite groups, the conformal group and the affine group. And then he goes on in another paper with collaborators to show that actually what we call GR is basically the theory of symmetry breaking of those two groups. And then you have the, from breaking those symmetries, you can see the metric as kind of like a goldstone appearing at that level. And so I thought it was very interesting that you recover conformal gravity or scalar gravity. I don't quite understand how, but I was also wondering if you could somehow try to recover affine gravity or Galilean, and if some combination of those two could actually instantiate Einstein's equation at this lower level.
This is a tough question. No, I haven't tried, so I don't know really the answer to your question. What I can tell you is that you can go and you can simulate a much more complicated system than the one for example, if you have a multi-phase BC, you can have a system which have multiple metrics. So bimetric, trimetric. You can simulate a situation probably where you have extra degrees of freedom. I mean, just have the metric describing the curvature. If you dope, for example, the system in such a way that, so definitely you can do more than the simple things that I've shown today, but I don't know the answer to your question, to be sincere, because I haven't never tried, and there is no way I can predict how it's going to go.
More questions or comments?
Maybe I can ask something. Is there a way in analog gravity, or is there an equivalent in analog gravity of the world entropy formula? And would you be able to detect when it fails or if it fails?
Unfortunately, no. You know, I tried, for example, to find the world entropy for Nostrum gravity. That was, but the fact that Nostrum gravity is not fully background independent because all the metrics are conformally flat, you immediately see that it doesn't work, the standard derivation, which is not so surprising because it's resting on different variants, right? So you really need to have a theory fully background independent, which is normally what we call a gravity theory. So it seems to me that that is abstraction. Is not, of course, definitely you can introduce an entropy proportional to the area. And I can even, I mean, probably this is, for those of you that are familiar with the derivation of Jacobson of the Einstein field equation, starting from the local Rinder frame that you can construct around any point of space-time, thanks to the equivalence principle, you can even follow that kind of path. And it looks like you can, but then you realize that you can't because it doesn't gravitate the stress energy tensor of the phonons, but just the trace at most. And that is crucial. And if you remember the fact that the stress energy tensor is conserved and it's what gravitates is strongly linked again to different variants, to the background independence. So it seems to me that this is definitely a limit of analog gravity. Analog gravity at most can provide you, with an hint of how you can emerge spacetime. For example, in group field theory, they do exactly a Bose-Einstein condensate, but from a theory of fields which doesn't live on space-time, it lives on a group manifold, and they can generate in some highly symmetric situation as space-time with the analog of a condensation. So this idea can be both, but in the case of analog gravity, you start with condensed matter system. The Bose-Einstein condensate per se set a preferred frame, and there is the metric of the lab. There is the container you cannot completely dispense. You cannot forget. So, but it seems to me that that is an hard way to go.
There is a question by Alex.
Thanks for the talk. So you mentioned this analogy between sound waves and massless scalar field in a curved geometry. Yeah, I was curious, is it possible to generalize this to beyond like massless scalar field, but have something like scalar field with two local minima, this kind of systems?
You can, for example, in a 2BC system, you have two excitation. One is massless and one is massive. And then in that case, you can have, for example, an analog of scalar QED. You have the scalar electron and a scalar photon. So you can generalize this. You can have a system like helium-3 where you have even vector excitation. There is even the claim that you can do spin-2 excitation. So in principle, yes, you can definitely generalize in a more complicated system. If you look at a book by Grisha Volovic on helium-3 analog gravity, you will find many of these other excitation you can simulate. There is a whole economy now also of quantum simulator, of gauge field theories and so on, which is, I think it is related, but it's not exactly what normally you would call traditionally analog gravity. But yes, the answer is yes, you can go much more complicated.
More questions or comments? So from people online? Okay, I think we had a very nice questions and comments answered by Stefano, and I think we can thank Stefano again for this very stimulating talk. Thank you, Stefano.
Thank you.
So there is still Fika here.